Confirm that you can see what's going on the screen. There is a lab, it's called Reversible Reactions Lab. Do you guys see it? When you see it, let me know. It might take a little bit time. Abhishek, all right. All right, so that's good. Abhishek can hear us clear now. All right, so now here we have particle control, and this is basically a reaction. You can see that this is on this side. This is the left hand side of a reaction. This is the energy hill over which the molecules must pass to be converted into product. Okay, so this side is the reactant side, this side is the product side. Here you can see the temperature. The reaction is very simple: conversion of A to B and conversion of B to A. That would be the reverse reaction. Okay, you can also control the heat if you want, increase or decrease the heat if you want. But we won't be doing that much, yeah, because we're going to keep the temperature constant, and at that constant temperature we will see what happens to the reaction. Does it move in the forward direction, does it move in the backward direction, by changing different species, okay, on A and B. Alright, this is a stop clock. You might need to use this because we want to see how long does it take for a reaction to achieve an equilibrium. Okay, so these are the test, these are the parameters of this experiment. Okay, so what I want you guys to pay attention is the scale. You can increase or decrease here. Yeah, you can make. So if you have, let's say, a situation like this, yeah, this is the energies. So on the y-axis there is energy, on the x-axis is the rate of the reaction, okay, or the progress of the reaction, how far the reaction has went. If the reactions are on lower energy than product, obviously the difference in the energy will be released, and that would be an the difference in the energy would need to be provided, because you need to the molecules need to reach this point for them to be converted into product. Okay, so that much of energy needs to be provided for molecules to jump. Okay, is that going to be an endothermic reaction or exothermic reaction? Okay, you need to provide the energy for there is a gap in the energies of the product and reactant, right? Reactants are at lower energy, products are at higher energy. Obviously there is a difference in energies of these reactants and products. Now if you convert the reactants into product, in this case you will need to provide this much of energy. Okay, I'm circling this portion. Well, I have to need to provide this much of energy because that is the difference in energy. Now right now here there is no difference in the energy in the products and reactant, right? But now there is a difference in energy, and this much of energy needs to be provided, and that should be an endothermic reaction, correct? Yeah, and if you change like this, if reactants are at higher energy than products, obviously you're gonna have to supply this much of energy. This much of energy will be released, and that is going to be your exothermic reaction. Okay, Abhishek, there might be something wrong with your connection. If it's too frequent, I don't know, you'll probably need to clear your cache, okay, before you start the class. I am actually wired. Oh yeah, for Abhishek. So all right. So what we'll do, we'll on this one we'll make this to 22 right here. Okay, this is 22 portion. Okay, so the product, so the reactants are at 22, and let's say the products are at 15. Okay, so we set this as the parameters. Okay, this is at 22, this is at 15, and now we'll add some molecules. Okay, so we'll add, let's say, 100 molecules of A. Now before you enter, hit enter, make sure that you pause. Okay, now you can see that the molecules are already there, but the experiment is paused, and then you, yeah, it is. I'm not doing anything right now. Okay, and then I'm gonna start the play button and start the stop clock at the same time. You can see that the reactions has started. The reactants are moving on the product side, that means they are getting converted. You can see the sizes or the ratios of A and B are converting. Temperature is going up and down, but it's fairly constant. Yeah, okay, do you guys see this? Okay, do you guys see this? Okay, so remember we started with about 100 molecules of A. Okay, at this stage we have about 25 and 75, yeah, on an average, give or take. Correct. So we have many molecules of A got converted into B, yeah, and some of the B are getting converted back into A. See that there, some of the B's are actually jumping back into the A. That's because for A to convert into B, there is a very small energy gap. Yeah, they need small energy, whereas for B to convert into A, there is a larger energy gap. So when the equilibrium is set, there should be more of B, less of A, and that ratio should be fixed at that particular temperature. Is that clear? Okay, so we'll wait for about I think let's restart the experiment. Yeah, so that's in case you missed the initial thing. Okay, what I've done is I've initially paused the experiment. Yeah, reset, and then I'll enter 100. Okay, play the experiment, start the stop clock at the same time, so you can actually see how long it takes for equilibrium to reach. Okay, so clearly this is a forward reaction. Yeah, the reaction is going in the forward reaction. You can see that the reactants are decreasing, products are increasing. Correct? Okay, so excuse me, so we'll wait for about 4 or 5 minutes. That would be about 300 seconds or so, and then we'll pause, and then we'll see. So if you pause the experiment, you can take the reading. Okay, you measure the reading and then let it go for some more time. You take the reading at different intervals of time, and you take the average of that. Okay, so right now it's still decreasing. You can see at about 300 seconds or so, it should reach an equilibrium. So you can see that now you have about 35 of A and 65 of B, and then we'll let it go. You can see that it goes down 33 of 67, so on and so forth. So you take an average of these two numbers. You do you take about 4 or 5 readings, take an average, and that would be your equilibrium concentration of A and B. Yes, temperature is still constant. It's about 300 degree Kelvin, 300 Kelvin. It's not exactly 300 because again the molecules are moving, the temperature is changing a little bit. That adjustment is going on at the same time. Okay, so now this is the important point here is that it's not like sum of A is converted into B. It's like sum of A is converted into B, sum of B is also converting into A, but at equilibrium that change is constant. Okay, so equal amount of A and B interconverting, that's the equilibrium. Yeah, that doesn't mean that the reaction has stopped at the equilibrium, means that the rate of change for A and B is constant. Is that understood? Okay, or other way you can say is that the rate of forward and backward reaction, so here the rate of forward and backward reaction is same, it's constant, and therefore the equilibrium has reached. Okay, so reaction is going in the forward direction, at the same time it is also going in the backward direction, but at the same rate. Okay, and that's equilibrium. Okay, and the equilibrium is decided by this energy hill. If you lower this energy for particle B, obviously you're going to have more B and less A. Okay, so you're going to you shift the equilibrium. Yeah, same thing if you decrease the energy of A, increase the energy of B, you can again shift the equilibrium in a different direction, basically depending upon how you change. All right, so let's go with these numbers right for now. Okay, we have 33 of A, okay, and 67 of B. Okay, and that's the concentration at equilibrium for these particles. Okay, what is the equilibrium constant? Can you calculate? Yeah, just have to go with this for today. Yeah, I can't help it. Abhishek? Okay, by the next class I will be at my home using my own internet. Okay, all right, you need help? Go ahead, Sahil. Okay, so equilibrium constant is around 2 for this reaction. Yeah, now let's keep that in mind, that this is the equilibrium constant for this particular reaction. Now reset this reaction. Okay, so we have already paused it. We'll reset, and now this time we'll enter 50 particles of A. Okay, enter 50 particles of A, start the reaction and start the clock. Okay, there are now only 50 particles, half the number of particles of A. And so before, or let me reset it again. Oops. Yeah. Okay, now what is the equilibrium constant, or what is the reaction quotient for this at this stage when there is 0 molecules of B and 50 molecules of A? It should be 0. Yeah, equilibrium constant is 0. Before we had equilibrium constant as 2. Now this is the reaction quotient. Reaction quotient is 0. In which direction? Reaction quotient is obviously less than equilibrium constant, correct? So in which direction the reaction should proceed? So we can predict this if we know the equilibrium quotient or reaction quotient. Because reaction quotient is low, it needs to achieve the equilibrium constant, needs to go to that number, correct? And so we should expect this reaction to go in the forward direction. Is that correct? Not endothermic or exothermic. Yeah, we're saying that, you know, this reaction is actually exothermic in a sense, but the reaction quotient for reaction at this stage we have 50. Why are these numbers? I don't know. But yeah, the equilibrium reaction quotient is 0 divided by 50 is 0, right? Equilibrium constant was 2, so obviously reaction quotient is smaller than reaction quotient equilibrium constant. And we know from our relationship that we studied in the class that if reaction quotient is smaller than equilibrium equilibrium constant, sorry, then the reaction goes in the forward direction, correct? And so let's see if that is the case, and start the reaction, start the stop clock, and we can see that the reaction is in fact going in the forward direction. Yeah, so let's wait for again few minutes, okay, about 300 seconds, see what goes on, and then we can calculate equilibrium constant. So we need to wait for now this reaction to go to equilibrium, and then we'll calculate equilibrium constant for this reaction, okay, and we'll see if that is the same as the previous reaction. Okay, it looks like if you see the numbers here, they kinda have reached an equilibrium, okay, maybe a little bit more, I guess, few more seconds. Okay, so about this one you can take few more readings here, okay, and then you can see the average is about 17 or so. Let's take one more reading. Yes, so about so to me the average is about 16 or 17 of A and 32 or 33 of B, okay, and with those numbers can you calculate the equilibrium constant? So now the reaction has reached equilibrium, okay, so with these numbers now can you calculate the equilibrium constant? What is the equilibrium constant for this reaction? No, product divided by reactant concentration, okay, product concentration divided by reactant concentration. (33) divided by 17, what do you get? About 2, correct? And that was the equilibrium constant for previous reaction when we had 100 particles. Yeah, so both of you guys are getting different numbers, so it's about 2. So that was the same equilibrium constant as before, correct? We had 100 particles, we had the same parameters, and we had the same equilibrium constant. We reduced the number of particles by half and we still get the same equilibrium constant, okay. So it doesn't matter the number of particles or the concentration, the equilibrium constant will be reached. Whatever the equilibrium constant is, that will be reached by if the reaction and the temperature and other parameters are same, then the equilibrium constant is same for that specific reaction, okay. That's the point I wanted to make. Okay, now we'll do something different. So let's say we want to reset this now, okay, and we have now we take, let's say, 40 particles of A, all right, and we take 35 particles of B. We start the reaction, play the reaction, and then start the stop clock. And so okay, so before the reaction we had let me reset, 40 of A and 35 of B. Okay, now at this stage, what is the equilibrium, what is the reaction quotient for this reaction now at this stage? Yeah, around, it's about 0.8 something. Yeah, now obviously reaction quotient is smaller than equilibrium constant. Okay, and again we expect the reaction to go in the forward direction. Now this is clear from the number of particles. You can see that there are more number of A's and then less number of B's. Obviously this equilibrium persists if there are more number of B's. Yeah, so you should expect the reaction to go in the forward direction, and that's what we expect. And let's see if that would be the case. Yeah, so we have already calculated the reaction equilibrium constant for a specific reaction, and so let's say start the reaction now, and let's see if we get the same number. We should, forgot to stop this clock. Yeah, we'll add about 15 seconds or so into the clock. Okay, and
हेलो मैडम, वो जो बड़ी वाली बीम आएगी ना हॉल में, वो उसका डायरेक्ट पासवर्ड चलेगा।
okay, so we'll wait for about some more time. Yeah, it should reach early because we already had some number of B's, and so it looks like the number stayed pretty constant at that level, and basically seems like the equilibrium has reached. Yeah, and so if we calculate the equilibrium constant at this point, what do you get? 50 divided by 25. Again, that's the equilibrium constant. Okay, is this clear? The idea how equilibrium constant is dynamic, or how the reaction is dynamic. It can go in both the direction, forward or backward, and that would actually depend upon this energy heal. Okay, all right, now reset all. Let's use 33 particles of A and 67 particles of B. Obviously, what is the reaction quotient here? (67), okay, over 33. Okay, what is the reaction quotient at this stage for these numbers? Can you guys hear me? I understand that there's a bit of lag there. It always is actually. Maybe today is a little bit more. Two. 67 of B and 33 of A. Yeah, so the equilibrium reaction quotient is at reaction quotient is 2, which is the same as equilibrium constant. That means the reaction is at equilibrium, correct? So if we start the reaction, the numbers should stay pretty constant, and so we don't actually need to proceed this reaction but let's see that the reaction will stay pretty constant. Yeah, see, the numbers will fluctuate a little bit, but we just take roundabout numbers, yeah, average numbers, so on and so forth. Okay. All right. What next? All right. So basically, right now the reaction is not behaving the way we expect it to behave. Yeah. The reaction, the equilibrium constant has switched a little bit. Probably the energy hills are not accurate or something. But you get the idea, right? I mean, if you let the reaction go so you can see now the numbers are kind of coming close to what we started with. Yeah. So this is the equilibrium. You can let the reaction go for any amount of time, but the concentration won't change much. It will be pretty constant within that range. Yeah. So that the reaction equilibrium constant will stay about 2. Okay, it may not be exactly 2, but it's going to be about 2, give or take some numbers. Okay, now if we pause the reaction, let's say, and then let's say if we remove 25 of A, and so so if we have 30 now, we just take 5. Okay, we remove 25, and that's so now we have we remove 25 particles, so now we have only 5 A particles. Okay, what is the reaction quotient now? With these numbers, yeah, 70 of B and 5 of A. Is that larger than equilibrium constant or smaller than equilibrium constant? That is correct, Sahil. It's about 14. So reaction quotient is 14. That's larger than equilibrium constant, correct? And so what should we expect the reaction direction? Should it go in the backward direction or should it go in the forward direction? Backward direction, that is absolutely correct, and let's see if that is the case. And so again, just restart the stop clock, and after some time we'll again measure equilibrium constant. For this we said the reaction quotient is 14. That should drop. Okay, some of the B should get converted into A, and obviously since A goes into the denominator, the quotient will drop until it will reach equilibrium constant, and that's when the reaction is at equilibrium. Okay, let's see a few more seconds, and it's not actually going very fast. I wish there was a forward button or something. Okay, let's stop the reaction at this stage and calculate equilibrium constant, and it seems like it's about 2. Yeah, and so we again reached that point where the equilibrium constant is 2. No matter what the reaction quotient is, if you let the reaction reach equilibrium, it will reach equilibrium constant. Clear? Okay, 2 points that you need to understand from this experiment is that what is the effect of reaction quotient, okay, how it shifts the equilibrium, how it forces the equilibrium or the reaction in the forward or backward direction. Okay, if reaction quotient is smaller than equilibrium constant, then the reaction goes in the forward direction. If the reaction quotient is larger than equilibrium constant, then the reaction goes in the backward direction. Okay, until you reach equilibrium constant. Is that clear? Alrighty. Now, give me 1 second. Let me think. What else we can do? All right. So let's do one last experiment. Let's start with 100 particles of A. Okay, and start the experiment. Let it reach equilibrium. Okay. So let's start the stop clock at the same time. Okay. Sorry for the disturbances today. I actually had a friend who had a nice cabin. So. Okay, so let's stop the reaction at this point, and let's say we add. So at this stage, we know what the equilibrium constant is. It should be around 2. Okay, now add about 25 particles of A here. Okay, so we add one by one. Basically, there is, or you can add how much? 35 plus 25. How much is that? 45, 55, correct? 60. So at about 59, so we add 25 particles. I think that is so we added 25 particles of A, okay, extra. So basically we added more reactant to it, and let's see what happens again. So before that, again the equilibrium, so the reaction quotient is smaller now because we added more reactant, right? So reaction quotient is smaller, and then we should expect the reaction go in the forward direction, and it should again reach that point where the equilibrium constant is 2. Okay, so whenever you calculate equilibrium constant or even the reaction quotient, they are basically the same thing. The only difference is reaction quotient is not at the equilibrium when you calculate Q. When you calculate equilibrium constant, you are saying the reaction is at equilibrium. That's the only difference. Okay, and just let it go for, I guess, a few more seconds, and okay, so short stop. Alright, so that's about 2 at this stage, a little bit off, but it's about 2. And so we again proving our theory over and over again and again. We added a stress. When we added 25 particles of A, we added stress to the system. Okay, and the system, according to Le Chatelier's principle, acts in a way to reduce that stress. That means more number of A needs to be converted into B so that they can reach the equilibrium constant. Okay, so you can add again, I don't know, you can add again so 20 more particles of, or you can double the quantity, I guess. So you can add about 80 of that, and so you can see that this is pretty much at equilibrium. You added more of A, the number of particles are same in this case, and if you let the reaction go for some more time, the A should reduce, the B should increase. Okay, we are adding stress here, and so let's wait for some time until it reach an equilibrium. When these numbers don't change by a lot, we can pause the reaction and see what the equilibrium constant is. Okay. Okay, that's you can see it's about reaching that point. Now if you pause the reaction here at this point, you again get equilibrium constant as 2. Yeah, we can add, let's say, 33 and 67. Pause, start. Now this is at equilibrium, this reaction is at equilibrium at this point. Now let's add about, so pause the reaction. Okay, pause the reaction and add about 25 more particles of B. Now we are now increasing the reaction quotient. Okay, remember that the product concentration goes in the numerator. That means the reaction quotient has increased. Yeah, or equilibrium constant has changed to reaction quotient, which is more now. Now Q is more than equilibrium constant. That means the reaction needs to go in the backward direction to reduce the stress. Okay, and this is the added stress, 25 particles of B we added. And let's start the reaction again, and you should see after a while it should go back. And so you can see the number of A particles are increasing. Correct? It's not decreasing now, it's increasing. Yeah, so more number of B particles are converting into A. Yeah, so no matter what stress, you can add pressure, you can add temperature, any stress. If you add, the system reacts in a way to reduce that stress. Okay, it will take the reaction in the backward or forward direction. Okay, and so now it's again kind of reached an equilibrium point. Make sense? Okay, I think that should clear all your concepts about equilibrium constant. Okay, let me minimize this lab.